All right. And we are back live. Oh, I got them talking. I got you knocking down things on her, wearing lavender. Like, yes. I understand. Somebody actually asked me that. Somebody asked me that yesterday. And I'll tell you the same exact thing I told them. We have not been given any updated instructions in regards to the guards, even though, yes, we are 6 feet apart. And until such time, the guards got to stay up, number one. Number two, if it was taken down and I allowed that to continue and then an administration person walked by, I'm the one in trouble.
What are we going to do?
No, they wouldn't fire me, but I would still be the one in trouble.
Yeah, but it's like, hey, don't do that. If you're in trouble, it's like, okay, I'm still getting paid the same amount.
Yeah, but then there would be a letter in my file, and then if that were to escalate and they wanted to get rid of me, eventually they could. If you get letters in your file, it's not something that docks your pay or that stops you from doing certain things on the job, but it is evidence that they could eventually use if they decided to get rid of me one day. There would be a letter in my file, and they'd be like, look, this is a series of disrespect and not following directives, and they would have that evidence to get rid of me. Oh, my word.
I'm just saying, if you're trying to work into the retirement, I'll send it.
You smell like lavender.
I know, right?
Anyway, ladies and gentlemen, listen very carefully. On Thursday, you need to make sure that you bring in your Chromebooks, charged, ready to go. On Thursday, as I have been prepping you for multiple class periods, I am not going to be here. I'm getting the second vaccination shot on Wednesday and taking the advice of people who have gotten that second shot. They have told me that the second shot, the after effects feel like a punch in the face. So I need to make sure that you are prepared and ready to go on Thursday. Who's in trouble? Mr. Mark is here. Yes, I do. Uh-huh. Does it smell like lavender? Okay. I know everything. Okay. It's fine. Bye-bye. You got to get your jacket at the end of the day.
Oh, yeah. Yeah, forgot about that.
So, on Thursday, and this is for those, again, specifically for those online, on Thursday, there will not be a live stream, but there will still be an assignment posted to Google Classroom that you are going to be responsible for. Now, yes, for those of you here in person, there will be a teacher or someone taking attendance, but since there is no live stream, this is specifically for those that are virtual students online, you need to make sure that you get that Google Classroom thing done so that I have evidence of your attendance for the day. That would be fantastic. Now, with that, knowing that I am not going to be here on Thursday, I had to rearrange a couple of things in what I wanted to do. I am going to be going a bit deeper into logarithm properties today. I know. But the thing is, because I know I'm not going to be here on Thursday, and because I know that you are going to be doing practice problems and whatnot on Thursday, I need to make sure that we have this information down today for logarithm properties. It is going to be a bit more note heavy today, but it's mainly because I know I'm not going to be here on Thursday. You'll see. Now, beyond that, I will remind you, as I have, you need to make sure that you are getting started on that project. Now, several people have gotten started on the project. Of the people that have emailed me, probably prior to like 5 p.m. yesterday, I have gotten back to them. If you emailed me after 5 p.m., I don't think I had time to get back to you. But you need to email me your selection for your car and your house so that I can give it approval and I can put it on the Google Sheet. because you are not going to be doing the same car and house as anyone else. When is your project due? Yeah, what day of the week? It's a Tuesday. The 23rd, right? Tuesday. Now, obviously, I assigned this thing last week. Coincidentally, I did not receive one email over the weekend. Okay, that's fine. Just do not wait for the last minute. Do not let it be Monday night, the 22nd, when I get an email from you. Do not let that happen. Because if I'm getting an email at 8 o'clock or 1 in the morning on Monday, I'm not going to be able to reply to it. I don't know. Yeah, I just decided to slack for a bit. But make sure that you are getting on top of that. Do not leave it for the last minute. Do not. That's up to you. Yeah, but the quality of your project may not be as good. So, all of that being said, since this is the last time I will see you this week, think about that, because I'm not going to be here on Thursday. I'm going to need those notebooks out and open. I say that, and you're like, oh my gosh, you're saying that again? And then it's going to be next year, and you're going to be like, you know what I miss? Yep. Your very specifics behind that statement make me very concerned about something that happened in your past. Let's see what we got here.
Probably notes, honestly.
So, for those of you in the chat, I should be able to see the chat if you have any questions in a few moments. I just got to switch over my screen right here. Today is the 16th.
Will I be able to knock out the 15 then?
Sure. Now, I will tell you one thing. I am probably one of the only math teachers in this country that do not like Pi Day.
Don't like what?
Pi Day.
Oh, my brother's birthday.
Pi Day, I feel, is a waste of time. Again, the guys are still talking over me. I feel like pi is overrated. Now, one might argue that, oh, well, all of mathematics is overrated because, we never use it. I've had that argument with you at the beginning of the school year, finding the glory in the struggle. But beyond that, the thing is, pi only really applies to perfect circles. Think about that. You calculate pi by taking the circumference of a circle and you divide it by its diameter, correct? Yeah, bringing back geometry flashbacks. But that only works for perfect circles. Not many times in life. There are some, but not many times in life are you dealing with perfect circles. Now, there are a couple other numbers. Number one, a number called phi, P-H-I. I dedicate an entire chapter to that in a class that I teach called Discrete Math. But there is another number that we are going to be learning today. A number called E. Now you may think, well, first of all, E, how is that a number? Well, how is pi a number? Pi is a letter, right? It's a Greek letter. Yeah. You get pi on your calculator right here. Look at this right here. It'll focus in a moment. It will. It's right there. You get pi on your calculator right there. And you know how to get that thing on your calculator. It's fantastic. You hit second and this caret symbol, and then boom, you got pi in your calculator. But I say E is much more important. Look what's written in yellow right below that pi button. You get an E, a yellow E. Now, on your Chromebook calculators, I believe it's in blue. But we're going to deal with that today. This E has everything to do with some of the more special properties of logarithms. Now, this is how important this E is. Yes, you have a pi button and you have an E button right there. Now, check this out. If I move the calculator over here, look what you have there. You have another E button. There are 2 dedicated E buttons on the front of your calculator. That is how important this thing actually is. And we are going to get into the details of that today. First, let's talk about some of the more basic properties of logarithms that I need you to be on top of. First and foremost, a reminder. The logarithm form, log base b of y equals x. Now, I want to emphasize this base. I want to emphasize this base right there. That base can be any positive number that you want it to be. That base on the logarithm is the same base that is on the exponential. When you are converting from exponential form to logarithm form, you need to start by understanding what that base actually is. We have a log base function in the calculator that allows us to pick the base in order to do proper calculations. But depending on what that base is, there is something called a common logarithm. There is something that actually is designated to be a common logarithm, and it is something in the lines of log base 10. Log base 10. Whenever you have log base 10, it is referred to as the common logarithm. Now, I could also write it down like this. What is the difference between these 2 logarithms?
Well, I mean, besides that, the base isn't written.
The base isn't written.
You can assume that it's 10.
Yes. Yes, you can. The statement, and I would have you write this down as well. I'm going to put a little arrow there. You don't have to write the base. If the base is not actually there, you have to assume, or you are allowed to assume that that base is 10. Now, why 10? Well, that's just what mathematicians designated it to be. Since it is what we call the common logarithm, they chose 10 as the base of it. Well, you got 10 fingers. We write numbers in a decimal fashion. You know? For example, if I wrote this, what is the symbol? How do you know it's a square root? Well, I didn't teach you.
It doesn't say otherwise.
It doesn't say otherwise. That's the key, though. Since there's no number here, since there's no number in that little crevice, you assume it's a 2. You assume a square root, right? Yeah. If you don't see a little number here for the logarithm, assume it's a 10. Assume it's a 10. It is known as the common logarithm. In fact, the button that is on your calculator, does not have a base written for it. If I were to zoom in on this right here, that log button is just a regular old log. Now, there is a reminder on the button written in yellow right here as to what base it actually is, but that is not always there. It's not. In fact, I'm very happy about this. Finally got a new phone for the first time in like 5 years. A Galaxy 20.
Why did you go with the Galaxy?
Because I prefer Galaxies.
Why?
Because iPhones are garbage.
Yeah, that's the way to go.
Okay. So this is the basic calculator that they give you with the phone. Whether you have a Samsung or an Apple, doesn't matter. You get this basic calculator, correct? Okay, just making sure. But if you turn that to the side and that thing turns over, you get a bit more functions. And if I zoom down a little bit right here, allow that thing to focus, you can see right there, there is a dedicated log button. There is a dedicated log button, but it doesn't have a base on it. And since it doesn't have a base on it, you have to assume that that log button is base 10. Hey, remember what I said about E earlier? I said E was more important than pi. Well, look, there's a pi button on the calculator. And there's an E button. And, oh, we're going to get there. We will get there. Trust me. It's part of it, part of this lesson today. But not only is E more important than pi, look, they gave E not only one, but two buttons. Why the heck would they do that? It's the same thing, except this one allows you to type in an exponent. But it's the same thing, essentially. It's just weird. But E is so vitally important that they gave it two buttons on this calculator. Insane. Now, if I were to do, let's say, I'm going to zoom in right here, log of 1,000. I'm going to hit enter in a moment. But you assume this is log base what? 10. Why is the answer 3? That's exactly correct. Let me repeat exactly what you just said, then I'm going to write it out. What she just said was, because what exponent would you put on a 10 to give you 1,000? That is absolutely correct. Because this is log base 10 of 1,000 equals some unknown, this would be, in reality, if you converted this to exponential form, 10 to the x power equals 1,000, which is exactly what you just said. And the only number that makes sense for turning 10 into 1,000 by raising it to a power, the only number that makes sense is 3. 10 cubed is 1,000. That is what that log button allows you to do. Again, that log button is automatically base 10. What function do you guys have on the calculator under math? What log function do you have on the calculator under the math button? You have log base. Now you have log base on your TI-84 calculators. You have it right math there. Log base, where you can type in the base yourself. Well, the thing is, my phone calculator does not have log base. This TI-83, watch this.
Wait, so on your phone you can only do log base 10?
Yes, I have a solution for that. On my TI-83, I don't have a log base. Yeah, I can only do log base 10. But there is a solution. Now, they call it the common logarithm. Again, log base 10, they call it the common logarithm because it is the most common logarithm that is used. But you can change that base to anything. There are an infinite number of numbers that you could put that base as. For your projects, you are going to need a very specific number there. Now, obviously, if you have the calculator on your computers, do it that way. We're fine. Do log base on the computer. You're fine. Go ahead. What do you mean, how high do the numbers go? Like, what's the largest number? Think of the largest possible number that you could ever imagine in your head. Are you thinking about it? Infinity is not a number. You got it? Add 1. It's bigger, right? Yeah, there is no largest number.
Where does it get to where they just don't have a name? Like 6
Names and values are two different things. Obviously, human beings can only name a finite number of things, but there are an infinite number of numbers. Yeah. What's really going to mess with your head is knowing that there are some forms of infinity that are mathematically larger than other forms of infinity. But that's a story for another day. So she asked the question, you asked about my phone calculator. You said, like, how am I supposed to, you only have base 10. How am I supposed to do it if I'm using my phone calculator? Well, this is where you have this, the change of base formula. The change of base formula. The change of base formula comes down to this. If you have log base b of y, again, doesn't matter what the y is, doesn't matter what the b is, but it's not 10. You just know it's not 10. It's not base 10. You can do what is known as the change of base formula, and I'm going to prove it to you. With this. Now, if you notice these two logs, what base are they? You assume they're 10, which you have a button for. And since you have a button for it, you can figure out any log base using this fraction. It's really fantastic. Go for it. Oh, actually, I want to write something else down, but go ahead. Well, let me show it to you this way. Let me show you an example, and maybe this will make a little bit more conceptual sense. Ready? Log base 4 of 64. Now, I'm going to type this into the calculator on my computer. I'm going to do the log base function to get that done. And I'm going to figure out exactly what that answer is using my computer in a moment. Let's see. Log base 4 of 64. It gives me a 3 because 4 to the third power is 64. Can we all agree that the answer should be 3? Okay. The answer should be 3. But, oh no, I only have a TI-83. How am I supposed to know that? I don't have a log base function. Well, if you do log of 64 divided by log of 4, if I do that correctly, it should spit out the same answer. It should spit out the same answer. And it will. And it will. Let me zoom in on my calculator, and then I'll zoom back out to the screen. Zoom in out, zoom in, zoom in, zoom in. Here we go. Here's log of 64. Oh, that's a really messed up decimal. Here's log of 4. Oh, that's another really messed up decimal. What am I supposed to do with those two numbers according to the formula? Not add them together. Divide them. So, log of 64 divided by log of 4, 3. Right on the dot. Because 4 cubed is 64. Check out my phone. Hold on. Turn my phone sideways. Here we go. I'll do log of 64 parentheses divided by log of 4 parentheses. Oh, look, 3. You can do it right on the phone. Yes? Dividing 2 of the common logarithms. The way that it works and the reason behind the way it works is, well, I'm not going to say it's very complicated. Let's just say it's something that you would predictably learn maybe in your second or third year of college if you were a mathematics major. You know what I'm saying? There is a logical way behind it, but the logical way behind it is it's a bit more tedious, so to speak. Let me try to show it to you. Well, where's my thing here? I'll do it up here. There's two different ways of looking at it. There's the second or third year of college way of looking at it is actually mathematically proving that it works. But I can just show you an example which kind of exemplifies it a little bit. So there's this thing up here. There we go. Here we go. So I would have 4 to the x power equals 64. Okay. Here's the basic example. There is, and again, I'm going to show you this property, but then you're like, okay, then how does the property work? Or why does the property work? You know what I'm saying? Again, second or third year of college. If I did log base 10 of the left side, and I did log base 10 of the right side, there is a property that we are going to write down in our notes in a little bit, which allows us to take the exponent and move it down there as a coefficient. Isn't that weird? But then I can divide both sides by log of 4. I can divide by log of 4, and I end up with x equals log of 64 over log of 4. It's very weird. It does if you understand why the exponent property works, which again, second or third year of a mathematics degree, but the property does work nonetheless. It's fine. Yeah. There we go. So, this thing. But again, look at these two decimal numbers. These two decimal numbers, it doesn't what the heck? Look at log of 64. The reason why log of 64 is that number is because 10 to that power is 64. And the reason why log of 4 is that number is because 10 to that power is 4. But when you divide those two decimal numbers, go ahead.
Oh, never mind.
What was the question, though?
Well, it wasn't even really a question because you said log to that number, and I was like, wait, what? And then I was like, oh, the answer that it gave us.
Yes. Yeah. I didn't feel like retyping it. But if I did actually retype it, look at these decimals. 1.806179974 divided by 0.602059913. What the heck?
For something so complicated, the answer is so simple.
Yeah. But it works. It works nonetheless. Zooming out. The answer to this is 3. Now, I have a note here for the next few properties that I want to show you. And this note is not exactly a star note. It's not exactly a star note. I'm going to give it an asterisk. Star notes are vitally important. This one's this is kind of important. For the following properties, you can assume the same base for all logs. I'm about to show you a few properties. And in those properties, you can assume the same base for all of those logs. And it is vital that you assume the same base for all of those logs, because they have to stay the same in order for the properties to work. Now, I'm going to say 2 words, and I want you guys to kind of define them for me. What does it mean to expand something? What does it mean to expand something? To grow. Give me more. So what? In a certain direction. What do you mean expand, though? I'm sorry, not, no pun intended, not expand on her definition, but what's another definition of expand? To stretch out, to kind of spread things out. What about to?
Build upon something else
Sure. What about condense?
to make it simple, small, tiny.
Exactly. The next couple of properties that I'm going to show you are the logarithm properties of expansion and condensing. Here's what I mean. Log base b of 2 numbers, x times y within those parentheses. Give me 2 numbers. Good job, crew.
9 and 4.
9 and 4. Okay, 9 and 4. And 9 times 4?
Oh my god.
36.
Why did math just leave my head?
That's okay.
We're doing logarithms and you're like 9 times 4.
I know, right? So check this out. Log of 36, right? Is this decimal? I don't care what the decimal is. But it's, and I can even do 9 times 4. Right? Clearly the same thing, right? No big deal there. No harm, no foul. Check this out. Log of 9 versus log of 4. Look at these 3 numbers. These 3 decimal numbers. There is a relationship between these 3 decimal numbers. What the heck is it? Ooh. This relationship might be a bit more exemplified if I did this. Check this out. Log of 1,000, log of 100, log of 10. What's the relationship between these 3 numbers? Kind of in numerical order, but I mean, I could just do it a different way, but how about this? Check this out. Remember I told you to multiply the 4 and the 9? I'm going to talk about this in a moment. Well, I chose this. They're not exactly all perfect squares. Oh, well, yes, but that's just because she gave them to me. Yeah. Ah. Now let me go back here. Log of 36, log of 9, log of 4.
9.9 something and 0.6 is 0.15.
Check this out. See how you kind of nailed it on the head. You know how you said they were like kind of added together? Right here, I got those 2 decimals, log of 9 and log of 4. Ready? It's the exact same thing as log of 36. This is a weird property. This is a straight up weird property. But what it allows us to do is this. It allows us to either expand or condense logarithms. It allows us to expand or condense logarithms. When you guys said expand, you're like to grow, to spread out, to make larger, expand. Yeah, that's when you split them up into separate logarithms. You could also condense them by putting them back together. But they have to have the same base. They have to have the same base. Notice the B's right there. They have to have the same base. So I could do some weird junk like this. Actually, you know what? I'm going to go to this calculator. I could do like math base or log base 5 of 10 plus math log base 5 of, give me a number that's not 5 or 10. 7. And it would give me this crazy decimal. I don't care what the decimal is. But because they're both log base 5, what's 10 times 7? We did it. It's so great. We did it. Same value. I know. I have my sister married a guy from the middle of Pennsylvania. And when you live in the middle of Pennsylvania, at a young age, you learn how to hunt early on. Oh, yeah, if you don't want to hear the deer story. Okay. My brother-in-law, he hunts a lot. And his first kid, my niece, obviously is a girl. Her name was Danae. And she, at the time, she's in high school now, but at the time she was like 5 or 6 years old. And my brother-in-law took her hunting. And he shot a deer. And this is what he was raised with. You kill a deer, you clean it up, you gut the thing out, you cut up the meat, you do what you got to do, right? It's the middle of Pennsylvania. So my niece eventually, like, you know, they're in the house or whatever. It's like a few weeks later, and she walks into the kitchen. Daddy, Daddy, I'm a deer. I'm a deer. And he's like, oh, yeah, you're a deer. She's like, well, shoot me. And he's like, okay. So he pretends rifle to shoot her. And she falls down, and she lays there for like a few seconds, not doing anything. And then she looks up. Now, cut me open. Like, yeah. But here's my point, though. When you're talking about a deer and you're cutting the deer and gutting it out, think about the deer's innards, okay? The innards. Now, if you think about the word innards, now think back to this. Because I'm taking the innards of the logarithms and putting them together. It's really weird. Or I could take the innards of the logarithm and I could split them apart.
Now I'm just thinking about deer guts, and that's weird.
Yes, but now you'll associate this property with deer guts. Anyway, back to this. One more. Log base b of x divided by y. Now, you could probably, I guarantee you, just based on the context of that first property, you could figure out what this second property is supposed to say. Based on the context of that first property, you could totally figure out what that second property is going to say. Yeah? Exactly. Yeah. It's just literally the same property, except it's now subtraction. Log base b of x minus log base b of y. It's the same property, except now, instead of multiplication and adding, you are doing division and subtraction. These properties, these actually two properties, are very, very similar to what we would do if it were, I don't know, like x cubed times x squared. What are you supposed to do with these two exponents if you multiply bases together? You add the exponents. Now think about that. Multiply the bases, you add the exponents. Multiply the innards, you add the logarithms. Same concept to if I did this. Now if I divide the bases, what do I do to the exponents? Subtract them. Same thing here. You divide the innards, you subtract the logarithms. It's so weird. Once in my life, I tasted deer jerky. It was kind of good. I'll tell you one more story about my niece. So for one of her birthdays, I think she was like 10 or 11, she got like a legit bow and arrow kit. And we were visiting for like Thanksgiving, and I was out of the house at one point. I was at the store or something, and I came back, and my wife is like, Danae shot a bird. And I'm like, what? Yeah, she shot a bird. I think it was a dove. And I'm like, well, what did you guys do? And she's like, well, she plucked off the feathers, gave it to her dad, and her dad, dressed it up and cut it up, and we ate it for lunch. That's how you do it. Oh, my word. It's the middle of Pennsylvania, One more. This is the property, actually, that we were talking about earlier. I think, Paul, this is the property that I was trying to explain, but it was like, again, the reason behind it is not really obvious, but it does work. Exponent, if you have an exponent inside of a logarithm, you are allowed to take that exponent and move it down to be a coefficient in front. Look at the exponent there. You could literally pluck it from where it is and put it in front of that logarithm. You are allowed to do that for problems. Notice what happens to the base. Stays the same. What happens to the y? Stays the same. Nothing else changes. Nothing else changes. It's literally, you can just take that exponent and pluck it out front. Or take a coefficient that is being multiplied by the problem, and put it up to be an exponent. It's so stinking weird. Logarithms and all of your weirdness and what you do. Gosh. Shooting birds. Taking names. Goodness gracious. My niece is, I don't know like how she finds time for all of this, but like she's an accomplished hunter. She's an Irish step dancer. And she's like a freshman in high school, but she's a really good like field hockey player too. Like what the heck? Goodness. Well, let me see if this sounds familiar to you then. My wife and I once said of my niece that if there ever was like a zombie apocalypse or some kind of disaster where their parents died, we always knew that Danae, no matter how old she was, she would like strap her brothers on her back. She's got 2 younger brothers. She would strap them on her back and find her way to New Jersey to find us. Just saying. She would be resourceful enough to survive. Just saying, that's the type of person she is. I got these 2 properties up here that I wrote down. I know you missed them when you came back. I'm going to leave them up here temporarily as I write the last couple before I get to some other stuff here. Because I got to get to E. Some very basic properties here. Check this out. Log base B of B equals 1. That is the weirdest thing in the world, but it works. It works because B to the first power equals B. That's the exponential form of it. The other thing is log base B of 1 equals 0. And that is because, and again, the reason why these properties work, because you have to understand the relationship between logarithm form and exponential form, because B to the 0 power equals 1. Those properties work in perfect unison. It's kind of like when you raise something to the 0 power, or when you raise something to the first power. Those are like identity properties. Yes, the B over C is just because I didn't feel like writing it out. Yeah, it kind of looks like a fraction now, doesn't it? Yeah. Yeah, no, you're right. I wanted to write out because, but I didn't feel like writing out the word, but now he's right. It looks like a fraction. But yeah, it is just because. Yeah. Let's see here. He's been virtual all year, up till now. Or for the vast majority of the year.
What is the log base y and
Good question. Let me show you something on the calculator. You ready? So like, I'm just going to use regular log base 10. Okay. Log of 36 is this decimal, right? We did that before. Now check this out. 2 times log of 6. This is the same exact calculation. And the reason why it's the exact same calculation is because I can change the 36 to be 6 squared. But because of the logarithm property, I'm allowed to take this 2, rip it out, and put it there as a coefficient. And because of that property, this calculation is the exact same decimal. But that's what remember expansion, condensing. Expansion would be putting it out front, and condensing would be putting it back in to be an exponent. It's very weird. It's like, remember all of the exponent properties that we learned in the past? It's like these are all like the inverse exponent properties. It's so weird. So stinking weird. But they work. All right, Let's talk about E. E is a number. E is a number that has been affecting your lives for years and years and years. It has been, whether or not you know it or not. The number E. See if I can find, there it is. I want to show you a brief video. A brief video about the number E before I really get into it. I have the microphone up to the speakers. Here we go.
We've made a video about pi, the ratio of a circle's circumference to its diameter. But there's a less famous, but equally fundamental number known to anyone who's taken high school algebra. It's about 2.71828182845945, and so on. And it was first defined by Jacob Bernoulli, but later Leonard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest...
Compound interest? Oh, what timing! We learned about compound interest.
...says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So, if you stick $1 into a bank account with 100% interest rate compounded annually, you'll get $2 at the end of a year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material. So, while E may not be as famous as pi, it's easily as fundamental and immensely important.
Yay! Oh wait, I already have it duplicated. I gotta go here. So what is E? First, let's go to the calculator. E is a number. E is a number. If you hit second division, you will get the number E. Now again, this number E is a fundamental number. This number influences the stock market. This number influences the reproduction rates of animals on this planet. This number influences the radioactive decay of elements. Governs it, really. Though the number E is heavily involved in the formulas that model them. Yeah. It's much more important than pi. Just saying. They don't use pi to calculate things within the stock market. They use E. E was mainly discovered, I say mainly because obviously there are other uses for it, as I mentioned, but it was mainly discovered through the compound interest formula. Someone get that? E is approximately 2.71828, and then it keeps going. Similar to pi, in which pi is a number that is considered irrational. Pi is a number that goes on forever and doesn't have a repetition. I mean, obviously, you might have like a 2 in there somewhere. Obviously, there's an 8 that repeats here, but there's no definitive repeating. Like, think of the fraction 1/3. 1/3 is 0.3 repeating. Do you guys ever learn how to do like repeating bars? No? Maybe? Some of you, yes? Yeah. Well, you can never put a repeating bar anywhere on pi, just like you can never put a repeating bar anywhere on E. Now, E, how in the heck does E relate to what we have been doing with logarithms? Well, do you remember what log base 10 was called? What name did we give to log base 10? The common logarithm. Well, there is something called the natural logarithm. The natural logarithm. And it is log base e. Log base e is what is referred to as the natural logarithm. Now, it is so fundamental. It is so natural to have that number e there. I kind of fibbed to you. Remember how I said that you can only do log base 10 on this calculator? I fibbed. You see the log button? Right underneath of it. That is an additional log button. That is the natural log right there. That is log base e. I'm going to show you that in a moment on the computer. Zooming back out. On the calculator, it is ln of y. ln. These two functions are the same thing. They are the exact same thing. They are interchangeable. Let me show you something on the computer, and then I have one more thing to kind of get down. So this natural logarithm, look right here. If I did log base, and I put an e right there, e, give me a 2-digit number. 22. And I get that crazy decimal. That's log base e. Basically, it's saying that e to that power, 3.091042453, e to that power gives you about 22. I would say it's rounded. It's rounded. In fact, I probably could have done this. Second enter, second enter. I could have done e to the power of the answer, and it would have given me exactly 22. Remember, e is that decimal. E is 2.718. That is messed up. A decimal raised to another decimal, and you get 22? What in the heck? But you do have an ln button. That is ln. ln is your log button that is automatically set to base e, and it gives you the exact same decimal. Somebody asked me the question about ln that they need to ask. Somebody asked me the question about ln that they need to ask.
Well, obviously, it's a natural logarithm, but on the calculator, it's ln, not nl.
Yeah, it's Latin. It's Latin for logarithmic naturalis. Yeah, logarithmic naturalis. Yeah, it's stuck. You can. I do have one more thing to write down, though. It's the last, literally the last page of thing I have to get down. So, the first part is a reminder. Remember, we did this formula for compound interest, and you have to do this formula for your project. N is the number of times compounded per year. You have to do this for your project. Well, here's the thing. If you're compounding monthly, if your bank compounds monthly, what is the value of N? How many times a year is that? 12. If your bank compounds daily, what is the value of N? 365. What would happen to the value of N if I compounded hourly? A lot more, right? What if I compounded by the second? A lot more. There are some instances of financial institutions compounding an infinite number of times. Now, Declan, you said before about infinity. I said infinity is not a number. How is it possible to compound an infinite number of times? It's not. They don't call it compounding infinitely. But if we were to do something called compounding continuously, meaning compounding in every moment of every millisecond of every day at every time of the year, if we were to compound continuously, we could not use this formula up top because we don't know what to plug in for n. We don't have a number to plug in for n. It would be an infinitely large number, so we can't do it. But if we were to compound continuously, there is an alternate formula. Instead of A equals the compound interest formula above, we have A equal to this formula, PERT. And of course, that E is the number 2.718 going on forever.
Like, I know we've already went over it, but like, re-say like what each variable.
Sure, absolutely, absolutely. If you want to go get that thing, get that thing. So, hold on 1 second. Before I do explain that, because I will, because I do have the time to do that. Hold on. Shh. Reminders. Thursday, I'm not going to be here. There will be something assigned through Google Classroom. You need to have your Chromebooks. This is your heads up. For those of you in the live stream, there won't be a live stream on Thursday. So you need to make sure that you see that Google Classroom assignment. Now, to answer your question about this, P is the principal amount. It's the initial amount that you put into it. This P down here, hold on, I'm still talking. You guys don't have to write this down, but I'm still talking. This P down here is the same P. This R up here is your interest rate. This R down here is the exact same R. It doesn't change. The T up here is the number of years that you leave the account alone. The T down here is the exact same T. The only thing that you can't do is the N. Because if you're compounding continuously, there is no number that you can plug in for N, so you just can't plug in that number. You can't use that formula. So instead, down here, we use the number E as the base of that exponential. According to the order of operations, you would have to take e to the RT power and then multiply it by P in order to figure out the resulting amount of money that you have. So it's weird, but that's where E comes into play. I gotcha. It's all coming together a little. I gotcha. Well, there's going to be the bell. If you haven't left a comment in the chat, make sure that you do. And I'll see you guys next week. No, you're fine.
But I got